We're going to learn what EMF means. Unfortunately, the name electromotive force, EMF stands for electromotive force. Unfortunately, it's a name that has stuck due to historical reasons. It's not really a force. So let's try and define it in a bit of detail in the following slides. Let's say you have a circuit and there's some kind of battery here that's trying to pump charges, negative charges, from one side to the other side. So imagine you have a conveyor belt. So this kind of battery is a mechanical battery, and the conveyor belt it attaches negative charges to it and pushes them by force from one side to the other side, and then lets them go over here. So the negative charges accumulate over here. And we've seen before in a previous video how an electric field is created inside the wires due to the positive and negative charges on the surface of the wires. So if you haven't seen this video, go back and watch that first. So as the charge is moving on the conveyor belt, there's the force due to other, I'll call F other. It's due to the conveyor belt itself, trying to push the charge opposite the way it wants to go. A negative charge wants to go to the left because the electric field is going from the positive charges to the negative charges. The electric field points to the right, so the negative charge wants to go away from the negative charges and go towards the positive charges. But there's this conveyor belt that's trying to push it opposite the way it wants to go. So the F other is the force due to this conveyor belt, and FE is the force due to the electric field that's trying to make it go to the left. So the work due to the other force to go from 1 to 2, it's integration of F other dot dr. This is just the definition of work. The EMF to go from 1 to 2 is defined to be the work due to the other force to go from 1 to 2 divided by the charge. The charge of each charge is minus E, the charge of an electron. E is positive, E is just the magnitude of the charge, and minus E is the charge itself. So this is what the EMF is defined to be, the work per unit charge to go from 1 to 2. And if I write the work due to the other forces in this way, then this is what the EMF is to go from 1 to 2. Now, assuming that the initial and final speeds are the same, the work due to the other force can be written as the negative of the work due to the electric field. So I can rewrite the EMF this way, and then the force on any charge is just the charge times the electric field. So I can take away the force and write instead of it charge, which is minus E, times the electric field. The minus E will cancel with the minus E. You get this relationship. You get that the EMF to go from 1 to 2 is minus integration from 1 to 2 E dot dr. E is the electric field due to the static charges that are on the conductors. Now this should look familiar. Integration of E dot dr, this is just should remind you of potential difference between 2 points. Specifically, it's V2 minus V1. So for an ideal battery, this is assuming we have an ideal battery, and we'll discuss a real battery later on. For an ideal battery, the EMF is just the potential difference across the terminals. If you get the EMF to go from 1 to 2, from the positive terminal to the negative terminal, it's the potential at the negative terminal minus the potential at the positive terminal, V2 minus V1. This is what you can write down the battery. This is the positive terminal of the battery. This is the negative terminal of the battery. The EMF to go from 2 to 1 is just the opposite of that. It's V1 minus V2. I just multiplied both sides by minus 1. So the EMF to go from 2 to 1 is V1 minus V2. It's a positive number. It's the potential here minus the potential here. This is what the symbol of a battery source of EMF is. They usually write it like this. The plus side is the longer and the negative side is the shorter. And the EMF of the battery, the magnitude of the EMF is written as epsilon. And so what we've just shown is that the EMF of the battery is just equal to the potential difference across the terminals. The plus side of the battery has a higher potential than the negative side by a certain amount, which is the EMF of the battery, the magnitude of the EMF. So this is basically how to relate then the potential difference across a source of EMF to the value of the EMF. And not all batteries, of course, work like conveyor belts. There are different batteries that have chemical reactions, like the lithium-ion battery, the lead-acid battery. Not all of them work with mechanical force moving the charges from one point to another point, but the idea is the same, that you can always relate the potential difference across a source of EMF to the value of the EMF of that source.